Let's add another layer of complexity to solving trigonometric equations. In this section, we'll make use of our identity formulas to first simplify the equation before solving. In example 6, we're going to find all solutions in a finite interval 0 to 2 pi for each equation. That interval indicates that we should be working in radians. On example A, we have two initial problems to deal with. First of all, notice we have two different trig functions in the equation. Second, notice we have different arguments in the equation, 1x and 2x. We'll use identities to remedy this problem. Notice cosine squared of x plus sine squared of x is our classic Pythagorean identity. We know that has a value of 1. So we can replace cosine squared plus sine squared with 1, and then we're dealing with a simple multiple angle equation. So we can solve this by isolating now our single trig function. We can solve for the argument by applying inverse cosine to both sides. We'll find the locations on the unit circle where cosine of x is equal to -1. That is, the x-coordinate on the unit circle is -1. This only occurs in one location, and that is at the angle pi. So our argument 2x can be expressed as pi plus any angle coterminal with pi. Finally, we can isolate the variable by multiplying both sides, including both terms on the right side, by the reciprocal of the coefficient. We obtain the complete solution, x equals 1/2 pi or pi over 2 plus, distributing our 1/2, k pi, where as always k is an integer. This is our complete solution. We're going to use that formula to generate the solutions between 0 and 2 pi. So we're working in an interval here. So the first solution, pi over 2, is between 0 and 2 pi. If we allow k to be equal to 1, the next solution would be pi over 2 plus pi. Pi over 2 plus pi would land us at 3 pi over 2. If I add another multiple of pi, we're going to have rotated beyond 2 pi. So the two solutions are at pi over 2 and 3 pi over 2. Recall that you could graph the original function and make sure that it has two x-intercepts in the interval between 0 and 2 pi to check your solution. You can also check each solution by substitution, but the purpose of examining the x-intercepts on the graph is just to make sure that we have found all solutions in that interval. Now, to save time, I'm not going to go through that again in this video. I'm going to focus on moving on to the next equation to practice the technique. On example B, we have sine of 2x minus cosine of x equals 0. Again, notice we have two different trig functions. And the bigger problem is that we have two different arguments. So we need to seek to express this in such a way that all of our trig functions have the same argument. Notice we have sine of 2x here. We could use our double angle identity to rewrite that as 2 times sine of x cosine of x minus cosine of x equals 0. Now all of our trig functions have the same argument. But what are we going to do about the fact that we have different trig functions? Well, if you notice, the two terms in this equation have a greatest common factor of cosine of x. So I can factor that out, and this leaves behind the factor 2 sine of x minus 1 equals 0. Observe now that we have the product of two factors equal to 0. We can then set each individual factor equal to 0. So cosine of x equals 0, or 2 sine of x minus 1 equals 0. This means that we have two trig equations, but each of those trig equations now only has a single trig function to evaluate. So we need to evaluate inverse cosine of 0, and solving for sine of x here, we can see that sine of x is equal to 1/2, or x is equal to inverse sine of 1/2. Now, because we're working with a non-composition here, or just 1 times x instead of a multiple angle equation or one that has a transformation, we can simply generate the solutions in one rotation of the unit circle. I am going to go ahead and write the unit circle to visualize these solutions. So first of all, where is cosine equal to 0? Cosine is equal to 0 at pi over 2 and also at 3 pi over 2. Then we can say, where is sine equal to positive 1/2? Sine is positive 1/2 at pi over 6 and 5 pi over 6. It's not necessary to express the complete solution, that is with the multiple of 2k pi, because we have already found all the solutions in one rotation around the unit circle. When I express these in set notation, I'm going to express them in order from smallest to largest. So we have pi over 6, pi over 2, 5 pi over 6, and 3 pi over 2. If we were to graph the original equation, we could observe it has 4 x-intercepts. Let's try example C. We have tangent squared of x plus sine of negative x equals secant squared of x plus secant of x minus 1. So we have 2 different trigonometric functions, and in one case, one of our functions has a different argument. Also notice we have the square of trigonometric functions, and on this side it's combined with a 1. So we should be thinking about our Pythagorean identities. On the left side, I'm going to leave the tangent squared of x as is, and observe that because sine is negative, sine of negative x is equal to negative sine of x. Also, notice we have the combination secant squared of x minus 1. We know from our Pythagorean identity that that's equivalent to tangent squared of x. So those two combine to make tangent squared of x, but we still have this secant of x term on the right side. At this point, we can then subtract tangent squared of x from both sides, and we will have lost one of our trig functions. We obtain negative sine of x equals secant of x. Now I'm going to go ahead and express secant of x as 1 over cosine of x. Then you can multiply both sides by cosine of x. And we have the product, negative, I'm going to write it in the order sine of x, cosine of x equals 1. If it were the case that the product on the left was equal to 0 on the right, then we could set each of those factors equal to 0. But because the product is equal to 1, we need to strive to express the left side in terms of a single trig function. Recall that sine of 2x is equal to 2 cosine of x, 2 sine of x cosine of x. I recognize that product on the left side, or a form of that product. So if I had a 2 on the left side, then I could replace that expression with a double angle identity. So I'm going to multiply both sides by not 2, but negative 2. Negative 2 so that I can have this product 2 sine of x cosine of x on the left side. That is sine of 2x equals negative 2. Now let's go ahead and apply inverse sine to both sides, and we're going to get an interesting result here. Recall that the domain for inverse sine is between negative 1 and 1. We're trying to plug in an argument here that is not in the domain of inverse sine. If I did this with the calculator and attempted to evaluate inverse sine of negative 2, the calculator would indicate domain error. So because of this contradiction, the symbol for contradiction in math is 2 arrows running into each other, we could say this equation has no solution, and that's always a possibility. Now, there's a little bit of uncertainty here, so how do we verify this with our calculator? Well, I'm going to go to y equals, I am in radian mode, and I'm going to graph the original function. Notice to type in tangent squared of x in the calculator. You can type it in tangent of x squared. The square belongs to the entire function, not the argument. Okay, plus sine of negative x. Now, I'm going to make sure all of my terms are on one side of the equation. So I'm going to subtract secant squared over here on the left side. But I can't type in a secant. I'm going to have to type it in as 1 over cosine of x. And I'm going to square the cosine to get secant squared. I'm also going to subtract 1 over cosine of x from both sides and add 1 to both sides. Now, we're looking for solutions between 0 and 2 pi. I'll just set the scale to be pi over 4. And let's see if we have any x-intercepts. Oh, we come close, but notice the graph does not cross the x-axis between 0 and 2 pi. Therefore, there are no solutions to this equation on that interval. That's a little bit unsatisfying, but sometimes it just works out that way. Let's try example D. We have cosine of negative x equals tangent of pi over 2 minus x. Let's simplify this using our identities. Because cosine is even, cosine of negative x equals cosine of x. And notice that tangent of pi over 2 minus x could be written in terms of its cofunction, cotangent of x. Now I have two different trig functions, so let's get some insight by expressing cotangent of x as cosine of x over sine of x. At this point, we can clear our denominator by multiplying both sides by sine of x. So the left side becomes sine of x times cosine of x, and the right side, when we multiply by sine of x, it cancels. Just in case you didn't see what happened there, let me go ahead and write it down for clarity. Just multiplying both sides by sine. Now, you may be tempted at this point to divide both sides by cosine of x, but if I do, I'm going to lose that factor cosine of x, and I could potentially lose solutions. So instead of dividing both sides by cosine of x, I'm going to subtract cosine of x from both sides. And then I'm going to factor the greatest common factor, cosine of x, out of the two terms on the left. Then, because we have a product of two factors equal to 0, we're going to set each of those factors equal to 0 and solve for x. Now notice we're dealing with a single angle equation. That is, the argument is x. So we can use our inverse trig functions here to generate the solutions in one rotation around that unit circle. So we need to find everywhere on the unit circle where cosine is equal to 0 and sine is equal to 1. Cosine is equal to 0 in two locations on our unit circle. Cosine is equal to 0 at pi over 2 and 3 pi over 2. Once again, because I'm not going to be manipulating these equations with the 2k pi, it's sufficient to find the solutions in one rotation around the unit circle directly. We also need the location where sine is equal to 1. Well, sine is equal to 1 at pi over 2. So the two solutions to this equation are pi over 2 and 3 pi over 2. If I were to graph the original function, of course, set equal to 0, I would see two x-intercepts between 0 and 2 pi. We could also verify those solutions using traditional substitution. If I plug both of those into the original equation, they would both balance the equation. All right, let's try one more. We have sine of x cosine of negative 2x, cosine of x sine of negative 2x equals negative 1/2. Let's start with our even and odd identities. Because cosine is an even function, cosine of negative 2x is equal to cosine of 2x. So we can simplify that argument. And because sine is an odd function, sine of negative 2x is negative sine of x. So I'm going to take that negative coefficient, combine it with the positive coefficient to make that a minus. So we have cosine of x sine of 2x equal to negative 1/2. Now let's take a look at the pattern on the left side. Notice we have sine times cosine here, cosine times sine here. Also notice that the arguments are in the same order, x, 2x followed by x, 2x. Hopefully you recognize this as sign of a difference on the left side. That is, we can condense it into sine of the first angle x minus the second angle 2x. Well, that's equal to sine of negative x. Once again, we can apply our odd identity to sine of negative x to obtain negative sine of x equals negative 1/2. Dividing both sides by negative 1, we have sine of x equals 1/2. Let's go ahead and apply inverse sine to both sides. So x is equal to inverse sine of 1/2. Now, because we're not dealing with a multiple angle equation, we can simply find all the solutions on the unit circle where sine is equal to 1/2. It's not necessary to express the complete solution, that is with the 2k pi, for a single angle equation. In one rotation around the unit circle, we can see that sine is equal to 1/2 at pi over 6 and also at 5 pi over 6. So we get two solutions to this equation, pi over 6 and 5 pi over 6. Both of those solutions can be substituted into the original equation for x to prove that it's a balanced equation. You can also graph the entire equation, of course, with the 1/2 moved over to this side, set it equal to 0. Check out the graph, you'll see that it has two x-intercepts. So even those identities that we practice in Chapter 3 can come in handy for these very technical trigonometric equations.